Start to share my screen. Just give me a second while my screen loads the PowerPoint. Okay, so thank you everyone for attending our webinar. So this is the webinar series 2023. This is going to be the second webinar in the series, and it's going to be on this topic of multi-phase volume of fluid applications using Simerics. So today is Wednesday, the May 3rd, 2023, and this is happening at 10:30 a.m. Eastern Time. My name is Chiran Srinivasan. I'm the branch manager in the Simerics Michigan office. I'll be joined by my colleague Varun Nichani, who also works from this Michigan office, and we're going to be taking you through this webinar. The outline of this webinar is going to be as follows. First, we will give you a brief introduction about our company, what makes us unique, what we bring to the table in terms of CFD and CAE. And we talk about specific to this current webinar, which is on multiphase volume of fluid approach, as to how Simerics-CFD can tackle this complex problem in real-world engineering applications. And then we will give you a VOF demo of a tank sloshing model that Varun Nichani will be going through. And then there will be two case studies. The case study 1 will be on an electric motor cooling. The case study 2 will be on a crankcase drawdown and oil ejection. And then we'll talk about the upcoming webinar. And then we will have some time to take any questions and provide any feedback. If you have any questions, you can feel free to type it in the chat box. And then at the end of it, I'll be able to answer that one after the other. So first about Simerics, we have 4 locations. So who we are we are engineers and researchers who want to produce path paving innovative technologies in the world of CAE. So far, we have provided engineers with robust, accurate, fast, and automated CFD tools for virtual analysis and design. Our goal is to cover CAE in a broader spectrum, and that is what we are working towards. We have 4 divisions. The main headquarters is it's a US company. The headquarters is in Seattle, the Washington state. We have an office in the Detroit suburb of Novi. This is the Michigan office in the US. And we have an office in Germany near Stuttgart. And we have an office in India in Bangalore. So how do we manage to do this? So we have 4 different things that we kind of put together to make our tool unique. So the first branch of it is the automated capability of the meshing. So we have a proprietary binary tree grid algorithm that automates the meshing process. This helps to handle very complex geometries as well as, let's say, easy to or tough to clean or dirty CAD geometries. And it can automatically mesh through those with ease. And it also provide different resolutions at different locations of interest. And that is something that can be done automatically with our mesher as well. It is the fidelity of the mesh that we get along with the solver helps in very quick turnaround in the model preparation, basically, also is in the model runtime. The second portion of this is the template-driven user-friendly workflows. So we have easy to use templates for various different applications, starting with pumps, compressors. Now we have a vehicle template, we have piston cooling template, we have fuel tank template. So any production heavy process, we can automate the workflow, and that can also help ease the use of the software as well as the model setup. So this makes it a very short learning curve for users and also very friendly for, say, design engineers to use the software. It also eliminates dependency on high-end development and reduces the manpower required to, let's say, clean up the CAD geometry or to create the mesh. The third portion of it is the ability to create moving and deforming and also dynamic meshes. We can model complex motions with For example, we have showcased our capabilities in the last webinar with the PT pump. We can model clearances, sophisticated gaps, like for example in the bearings with quite a good resolution of the mesh and with our automated workflow. And on top of that, we have a fast and a robust with an accurate solver. So it helps in fast conservation and convergence of physics in complex physics like in cavitation or multiphase or in conjugate heat transfer. And this makes us multiple times faster than other general purpose CFD code. Also, we have validated our tool across various different applications, and that is also something that we will be showcasing today in our case studies. So regarding to our software suite, we have 3 different software suites that we are currently developing. The Simerics CFD has been a platform that has been there for a while now. The FEA platform is relatively new. We've been working on this last several years, and we have come up with a platform that is now ready to be used. And also there is an optimization platform that that is also coming up in the next release that is going to be an inbuilt in-house optimizer that is strongly coupled with our CFD software. In terms of the CFD, we have multiple physics that we can address. The multiphase VOF is something that we will be talking about today, the cavitation physics, the heat transfer turbulence. And a latest branch to it is also been the Simerics integration with the CAD packages, as well as with different resellers. So we have now CAD kernel integration with Orca 3D, Creo, SolidWorks, Cases, Fusion, NX is our latest add-on. We also talked together with CF Turbo Cases, GTI with SimScale. So we have multiple, collaborations, and since the software is being utilized widely, so we have been working together to make it work in those platforms as well. So now let's talk about Simerics CFD for multiphase VOF. So I think volume of fluid has been there for a long time, but the commercial use of volume of fluid to track the different phases has been recently been utilized in a very wide variety of applications to get commercial value. There are a multitude of challenges that comes up with using this in an engineering platform where you're trying to do real world applications. One is that you have a very tough time to create a very sharp interface or capture a very sharp interface because you are looking at models that are very complex. You don't have probably the resolution sometimes you need to run these models with the mesh that you are using. Or in some cases, you probably have very small clearances where you don't have ability to resolve it very accurately. Also, it's been known that you can, especially for lighter phases, you can create or destroy the mass of those phases very easily if you don't, the solver doesn't address those things efficiently or properly. Also, it's been known to have issues with robustness in terms of when you run real world applications, you want to make sure that it can be able to run without the solver diverging at some point, so that you don't need to babysit the process through. Let's say you manage to do all this, you refine the mesh, you reduce the time step, you make sure it doesn't diverge, but the end effect of it can be that you will be running it for a very long time, and that is also undesirable where you are looking at fast turnaround times. To top it all off, if you are looking at a problem like this where you're looking at a crankcase drawdown process, you have the pistons moving, the crankshaft rotating, and the motions are very complex, and you want to do all the above for such a process. It it adds a lot of complexities to the already challenging problem. So having said all this, I think this is aligned to what our company is driven by. We want to create technologies that are there, let's say in the literature. We try to take it, we find a way to make it better, and we implement it in an engineering sense that can be utilized by the industry. So we have come up with techniques that can help address each of these concerns, and we have done this effectively. So our high resolution interface capturing scheme, coupled with our Cartesian mesh, can produce very sharp interface between the different phases of interest, as you can see in this example. So the pink or the magenta is oil, and the blue is the air, and you can see this is cranking. The crankshaft is rotating at about 4,000 RPM here, 4,000 about 4,000 RPM, and you can see that you don't see the interface between the oil and air diffuse at all, even though we're running this for quite a number of revolutions. We have explicit VOF with adaptive time step. So this lets us sub-time step. So we are solving the VOF, the volume fraction equations in a separate sense. And so this doesn't limit us in terms of our interface capturing requirements. While being able to run the simulation fast, we can also ensure that we conserve phases and create a very sharp interface between the different phases. Also, we ensure that we always satisfy the Courant number being one criteria. And on top of that, the way the solver has been written, it's of utmost importance to us that we have a robust solver which doesn't break while you're running your simulation. This is something that some of our users have a lot of happiness involved using our software. We see that it rarely has any trouble with convergence if they follow the set of practices that we have developed and help them implement. And also for complex motions, we have improved our numerical algorithms to ensure that we can address this without any of the above being compromised. So I'll briefly describe each one with an example. So the first one is multiphase interface capturing. So you're looking at an example of an electric motor where your shaft is spinning at very high speeds, can be about 10,000 to 20,000 RPM. And you are inputting flow, which is very low, let's say 1 to 2 LPM. And then it comes out and forms like a free stream and goes and splashes on this end ring surface. So this is a very tough combination for VOF because you have very small amount of flow coming at very high speed out of a very thin hole. And you can see the interface that we capture here is extremely sharp between the oil and the air. So it shows that a tough engineering problem in the real world can still be addressed using a software with a very reasonable time frame. The next example is for the explicit VOF with the sub-time step. You're looking at a coolant system filling scenario. Here it's a vacuum fill process. So what it involves is initially evacuate the system to 90 kPa below atmospheric pressure, and then you're filling in coolant at atmospheric pressure at the top boundary. So initially there is a huge pressure gradient of 90 kPa that creates a velocity in the order of 200 meter per second. So there's high velocity at the beginning. And then as the system starts to fill, the velocity starts to reduce. In this process, you don't want to sit and manually input different time steps as you run the simulation. So we use our explicit solver with as internal sub time stepping. So it does an adaptive time step to ensure your time is changed as a function of your Courant number. And this ensures that the interface that we capture, as you see here, is between the coolant and the water is very sharp. And also you notice here that we have been running this simulation for quite a long time. We run this typically 15-20 seconds. And in order to run this within a very fast runtime, this explicit sub-time stepping is something that can accelerate this process very fast to get results. So here you're looking at the next aspect of it is conservation of individual phases. So here the coolant is a constant density, whereas the air is ideal gas law. So when you're filling the system, when it's done filling, you should get to 90% fill because this is just based on the conservation of mass. So we see that the integrated mass error that we get is within 4% after we run this for 15 seconds. And you can see that the volume starts to saturate after you run this for a while. So this kind of shows how good we can conserve mass, even though we run this for a long time and do this aggressively. So next advantage I want to talk about is the necessity of the Courant number being 1, being always satisfied. So here you're looking at an example of coolant system fill as well, but here you're looking at the pump on filling. So when you run this case, initially you gravity fill it, and then you start to spin the pump. And you can see the curve here showing the different pump speeds. So you can have multiple pump speeds. You can see initially we start at 2000, then we ramp it up to 4000 odd and stay at that number. During this multiple speeds of the pump, we control only the external flow solver, which uses the same time step. And our adaptive time step makes sure that the Courant number 1 criteria is always satisfied. And this is automatically done by the solver. And this is what ensures that our interface capturing is sharp while our mass conservation and the final part of it is complex mesh motion. This is an example of a crankcase drawdown model. So the piston's moving as well as the crankshaft rotating. On top of it, we have a chain that is also moving. So all this is being modeled with oil and air physics, and the rotation speed being quite high. And we can do this very effectively using our VOF tool. I'll be showing this case study a little bit more in detail later on. At this point, I want to stop here and hand over the controls to my colleague, Varun Nichani. He will be going through the VOF demo.
I hope you can see my screen.
Yes.
Yeah. Good morning, everyone. Yeah, thanks, Chirant. Today, I'm going to go over, how to set up a tank sloshing model in Simerics. So before we get into it, I just wanted to give you an overview of the model we are going to set up. As you can see on the screen, this is the model of a tank, which is partially filled with water and rest of it is filled with air. And we are just going to be displacing this tank. It's going to be an oscillating motion along the y direction. And the idea is to, to predict the flow patterns and to study the sloshing inside of the tank. So let's get into it. So to begin with, what I have here are the CAD surfaces of the tank, which you can bring in from any CAD package in STL format. And just to get a sense of, the dimensions of the tank, basically along the y direction, which is the biggest dimension here, it's about 0.9 meters in length. And in the x direction, which is the thickness direction, it's about 0.1 meters. So fairly typical of a fuel tank inside, inside of our automotive vehicles. And to begin the model setup, the first step is to generate the mesh. So we go into our general mesher, and then we are going to add these surfaces. And we're going to use a relatively coarser mesh size for today's demonstration purposes. But at the same time, something that will give us fairly reasonable results. And then we're going to generate the mesh, and in a jiffy, you can see that the mesh has been generated. We're going to just do a quick inspection of the mesh to make sure everything looks good. And we'll double check the cross section. So it's a fairly reasonable mesh, right? The total cell count is about 134,000. So relatively a really small model compared to the size of models that we run these days. Next, once we have the mesh generated, the next step is to assign the physics modules that we need to solve for in this simulation. So this is a classic multiphase VOF problem where we have two fluids sloshing. So I'm going to include the multiphase VOF solver. I'm also going to add the turbulence model to account for all the turbulence that occurs due to the sloshing. And with that, I think, yeah, we are good with the flow physics. And quickly, we are going to set up the numerics for this flow module. Our best practice is to use second order upwind for the numeric scheme for better accuracy. And also we want to include the effect of gravity. So I'm going to turn the gravity force on, which is going to be downward, so minus Z. So I'm going to specify a value of 9.81. Next, I'll move on to the multiphase module. So by default, Simerics adds two components to the multiphase model. So I'm going to rename this to air, and the second fluid is going to be water. And we are just going to use the default settings in our multiphase solver. So we use the explicit scheme. We have the Quran number set to 1, and we use this adaptive Quran number method where we cut off the Quran number at maximum Quran number at 10. And next we'll go on to the turbulence model. Turbulence model, pretty much we use all the default settings. I would just change the convergence criteria to 1 because we are mainly interested in solving the flow parameters to converge to 1. Turbulence usually does not play such a big role in convergence. So having done that, the next step is to assign the material properties. So we select the tank volume, and over here in the properties panel, I'm going to assign the air properties. In this case, it's going to be a constant density of 1.23 kg per meter cubed. And for the water, I'm going to assign a density of 998.2. So fairly typical values. And then coming on to the flow module, we need to set the viscosity. So for air, we're going to set a value of 1.8 E minus 5. And for the water, it's going to be 0.001 003. Again, standard values at typical standard conditions. And we are also going to include the effect of surface tension for water. And the surface tension is going to be 0.073 Newton per meter. Lastly, we are going to come into this multiphase to define the initial condition to initialize our domain with water and air. So I'm going to initialize with a value of A0, which is basically an expression to define the level of air, and W0 for water, which I had already populated inside of this expression editor. So it's a fairly simple expression which just defines a Z coordinate above which it's going to be water, and below this level it's going to be water, and above that level it's going to be air. So it's a fairly simple expression here. And yes, after initializing the domain, we are pretty much set with our volume conditions or assigning the material properties. Next, we need to assign for the motion of the tank. So to do that, we are going to use this volume remesh option, and we are going to use the displacement, or rather the translation option, and we're going to provide a displacement to this tank, which is specified by this variable here, which is nothing but a very simple expression again, which is just an sine function with a certain amplitude and a frequency. So it is a function of time. So it's a reciprocating motion. It will move from left to right and so forth. And also, this volume remesh only takes care of the mesh motion. We still need to provide the actual velocities on the wall so that we can account for the shearing effect on the fluid. So to do that, we select the boundaries, and in this wall kind of boundary condition, it's we're going to change the stationary wall and specify a Cartesian velocity on this wall. So we're going to assign a velocity of Vy, which again is nothing but just the differentiation of this displacement so that we get the velocity. Again, a fairly simple expression. Having done this, lastly, we just want to enable some outputs. So I normally like to enable most of these integrated values. It just helps us, to give more insight into our simulation. And also, it helps us to maybe cross-check to make sure everything makes sense. So I'll just enable some, common outputs, which will also help us check for the masses of different components inside of our domain. All right. Yep, I think with that, we are pretty much set up the model. So just to quickly summarize, we started with the CAD surfaces. We generated our mesh using the general measure option, And then we just add all the physics modules that we want to solve for. We define the two fluids that we are solving for. And then we assign the material properties for the two fluids, which includes the density, viscosity, surface tension, and also the initialization of our domain. And lastly, we assign the velocities. And next, we are ready to run the simulation. So this is going to be a transient simulation. We are going to run it for 14 seconds with a total number of time steps of 2000. And number of iterations per time step, we're going to leave it at 10. And we're going to save the results every 50 time steps so that, we can create an animation. And before we run, let's quickly save this project. I'm going to save it as with today's date, May 3rd, and we are ready to run the simulation. So you can see that the simulation has already started running, and I'm going to quickly create an ISO surface to see the volume fraction of water. All right. I'm going to hide the CAD surfaces here. And then let me give a realistic color to the water. And then add some transparency so that it looks better. We can see through it. Maybe I can plot the pressure on it. All right. So you can see, I'm just going to leave my cursor here. You can see the tank moving, to the right. And as the tank moves to the right, you can see the water sloshing to the left. So this model can run really fast. You can see I'm running on it's a desktop with 32 cores, and it runs really, really fast. So in about a minute, it completed 1 second of, the simulation, and we just need to run 14 seconds. So it takes about 14 seconds to run. So while the simulation is running, I quickly want to go through some validations that we have for this particular model. This is actually a paper written by the folks at University of Naples in Italy, and they had it in collaboration with Fiat Chrysler Automotive in 2018. So they actually had a test bed that looks exactly like the model we set up here. And of course, for that model, they used a relatively finer mesh, but still it was, the total cell count was about 1 million. And they did some comparisons for this model. So I'll quickly go through these images here. And over here, they're comparing the ISO surface of water as a function of time at different instances of time, and compare that with the experiment. So as you can see, at different intervals of time, when the water sloshes from right to left in all the different scenarios, the ISO surface matches pretty well to the image from the test, right? This is some pretty significant sloshing, and we capture these patterns pretty well. And in addition to this, they also did some comparisons, some quantitative comparisons where they measured the center of gravity of the fuel tank, and they compare it with the experiments. And you can see that the two curves basically, line up pretty well. We get pretty close agreement between the experiment and the simulation. And all of this simulation was done inside of Simerics. This is for the X displacement, horizontal, and this bottom plot here is for the vertical displacement. And they did the test at two different frequencies, at 0.5 Hertz and 0.7 Hertz. So we get fairly good agreement. And the overall standard deviation was about 2.2% for the center of gravity. And in addition to this, we also compared the free surface of the fluid. So we just extract the top free surface curve and plot them for, the experimental versus the numerical result. And again, the two curves were quantified by outputting the standard deviation, and the error was within 4.2%. So we get pretty good agreement even for such a such a small such a small model, and it runs really, really quickly. They ran the simulation in like in 2 hours. So we are able to produce really good results in a really fast time. All right. Yeah, I think that completes this demo. I will hand it back to Chirant.
Yeah, thank you, Varun. Let me share. So thank you, Varun, for that nice demo. So now we talk about the engineering benefits of using the volume of fluid approach in studying real world applications. So the first one is the electric motor cooling. So this is a work that we collaborated with General Motors, and they were kind enough to share us some data so that we can do the study. So we worked with them to do this study with the GM research. So the objectives here was to predict the oil distribution across the different stationary and moving components, the windings, the rotors, and then look at the transient and steady state temperatures on the different components, mainly the windings and also the rotor and stator laminates. I think the electric motor model nowadays, I think everybody has a good amount of familiarity with it. So these are the different components that you are looking at. The main components to be highlighted are the windings, the end rings, the stator and the rotor laminates. So you have a shaft, which typically has also oil coming through there. So we'll describe a little bit about the flow here. So you have a rotor flow inlet. The flow comes in through the center hole in the shaft, and it kind of takes a path that turns 90 degrees because they have drilled holes on the left side and the right side. So they have the weld side and the crown side. And you can see that the space all within this cylindrical domain is spinning. So those are all the rotating components here. And so what will happen is the flow comes out and it kind of splashes on this surface. So there'll be some heating that is happening in the inside. The rotor gets hotter, the magnets inside gets hotter. So all that heat typically will conduct through this solid surfaces and gets cooled by this oil that splashes on the surface. The same thing on this. There is also another path that the oil goes through. That is, the oil comes from the upper sum. It takes a beeline through these channels and then splashes on these windings. So if you do a section cut through this minus Y view, you can see the crown side windings. The oil pouring from the top. They have a baffle that kind of has oil holes that can channel the oil to different locations so that you have a more uniform distribution of this oil coming through. And then if you look at the plus Y view, you have the weld side. Again, you have a baffle that kind of makes sure there is a distributor that distributes the oil equally. The gravity, as you might logically expect, is acting in the bottom direction, top to bottom direction, in the negative Z direction. So this is an animation of showing the oil distribution, 0 being air, 1 being oil. And you can see our interface that is getting captured as this oil comes through and goes through to this crown side and to the weld side. We even see that there is a phenomena where the oil comes and there is too much velocity here, which causes a jet that kind of siphons off some of the oil to the outside. So these things, I think CFD typically has a good perspective of visualizing, which could be hard to see or hard to expect in reality. Also, you see that the baffle that was designed here actually channels some of the oil that is coming through to the weld side back to the crown side, which is also interesting. So you would expect that you get equal distribution, but some part of the oil, travels back to the crown side, making it a little bit uneven, which is also something that CFD can offer a perspective. The extra, importance here is basically you have this electric motor that is having two different time scales because you're looking at the solid heat transfer that happens over a very long time frame. While you have the fluid heat transfer that happens over a much shorter time scale because the fluid flow is happening over a much shorter time scale. So we need to come up with an algorithm that effectively couples these two processes such that you can proceed through the heat transfer process in a very reasonable time frame. So for that, we actually created an extra algorithm. We wrote that again from scratch, and this is a module that is now available in Simerics. It's called a data exchange module. So what that does effectively is it transfers the HTC from the fluid with a reference temperature to the solid model. And the solid model is run with a steady state formulation, and we get update in the temperature, and we feed that temperature back to the fluid model as a boundary condition. And this process is done iteratively. Plot here visualizes this process in detail. So initially, you start with the flux on the fluid side, the flux on the solid side being imbalanced because you will have the solid at some specified temperature to begin with. And then you will start to exchange back and forth as you run this fluid model. You will run the flow along with the heat transfer, and you keep updating the H fluxes and feeding that as HTC reference temperature to the solid. And you'll see that the flux starts to slowly converge together. So the orange line and the blue line, the summation of it, which is the gray line, starts to go towards zero, which is what you would expect as the simulation achieves quasi-stable behavior. So again, this is a module that is available to be directly utilized. There is no scripting or external intervention needed. So all you will need to do is assign all the boundaries here as mixed scale coupling and all the boundaries inside here as mixed scale coupling, and then they will be transferring information back and forth as you run the model. Also, we run this again with an explicit time scale, explicit approach. So the VOF is explicit as well as the heat transfer is explicit. So this is an algorithm that is unique to our CFD software, which also helps accelerate through this process. So here I kind of show some contours of the temperatures on the different solids. This is the windings of the electric motor. As you might expect, the top portion is where the cold oil comes and splashes on. You'll see a colder region over there. And then the hotter region happens to be on the bottom portion where the oil doesn't directly get through. So it is the oil that kind of seeps through these windings that falls down is what is removing heat from these spaces. And naturally, the oil is already warmer by the time it gets to the bottom side, and it's not as effective in removing the high temperatures in this side. So the results that we get are aligned to what you would intuitively expect. For the stator laminate, this is the temperature distribution. And you can see the end rings that we have superimposed on the stator laminate. You can see a cold spot, the blue spot here. This is where the oil splashes on this end ring. So this is where you will have cooling that directly happens due to the oil splash. The final one picture here is the rotor solid. So the rotor solid here is essentially having heating that is happening on the inside with the magnets getting hot as well as heat source on the rotor. The cooling is happening through, I explained briefly before, through the conduction path to the end ring, this solid here, which is kind of splash cooled. And so the heat transfer path is not through this side, it's rather to the corners. So that's why you see the colder regions in the corner, while the hotter region is concentrated towards the center of this rotor laminate. So the next slide here describes a comparative plot that we got with the test or the experimental setup. So they had thermocouples that were placed periodically on different portions of the windings, both on the crown side and on the weld side. So they had about 24 total thermocouples. I'm cutting a plane through the Y on the negative Y space and the positive Y space in some sense. And you're looking at the measured thermocouple in our simulation in the red and compare that with the test in the green. So we can clearly see that wherever you have the dip in the temperatures, we capture that perfectly. And wherever there is an increase in the temperatures, again, we capture that quite well. So you can see like a sinusoidal type of curve for us, which is what the test also shows. And if you compare individual points and characterize this difference between the test thermocouple temperature and the simulation thermocouple temperature and do an RMS temperature difference, we are seeing our results to be within 9K of the test. So which gives us a lot of confidence in the numerical fidelity with which we have captured our results. So the next case study is crankcase drawdown and oil ejection. In this model, there are multiple interests. The model is very sophisticated, so I'll try to do justice by briefly describing this. So we have this full engine model. So you have the crankshaft that is spinning at certain omega. You have the pistons that are moving based on this omega. We have also the cam bearings, the main bearing, the rod bearings, all those have inflows. You can see here we have some inflows that are being prescribed in those. So we are also making sure that we spin the cam bearings. So here what we are doing is we are picking up oil from this pickup tube, and of course we are imagining this oil going through this high pressure circuit and then coming back through these bearings as inlet to our domain. So the inlet to our domain is all these bearing inlets. And then the outlet to our domain is the pickup tube outlet, basically. So what we are doing essentially is taking out the flow that we are putting back in. So at balance, the system will have the same amount of oil that we begin with. Only thing is the oil will redistribute itself to different locations. And the motion of all the systems will dictate how much oil gets held up in different portions of the system and how much oil gets collected in the sump. And we also have two open locations. One is this fresh air vent, which is open to atmospheric pressure, and the other one is the PCV, which is also open to a different pressure, basically. So the animation kind of gives you a good feel for what this problem is. So here I'm showing two animations, one at 1000 RPM and one at 2800 RPM. So what you're seeing here is oil getting pulled up from, let's say, the pickup tube through to the pump, and then we are inputting it back to these bearings, right? And you can see as the oil comes through these bearings, it creates a pool at the head. So the head is kind of scooping and keeping some oil. And then as it saturates itself, you'll start to see that the extra oil starts to move down. And now how they design these channels is very crucial to how much oil is getting held up in the system and how much oil comes back down to the sump. So if you're running this system or this engine at 4,000, 5,000, 6,000 RPM, you can start to create a lot of air oil mixture in the system. As you can see, from 1,000 to 2,800 RPM, you can start to see a lot of mixture of oil that is moving around. So at really high speeds, if the design of this is good, you will start to see you will see that you are able to pull down the oil, and then you can always feed the oil back to the sump. But if your design is not appropriate enough, you will start to hold a lot of oil over, and that is where you will start to excavate the sump out of oil, and that is where the engine runs into trouble. So one of the objectives of the problem is to study what is the level balance of oil in the sump, and as a function of speed, is this something that Simerics predict? And also the other part of the problem is you have a fresh air vent here, and as you try to crank the system, you will start to see some oil getting ejected through there. One extra objective to see how much oil potentially is lost through that air vent, and that can be higher at higher speed as well. I show a little bit zoomed in picture of the animation. So it's a really nice looking animation. So I just wanted you guys to, visually appreciate what is going on. And you can see here that we are running the simulation for a very, very long time in terms of CFD requirements. This is quite a long time. You can see 340 revolutions. And we still conserve phases excellently. And we don't have any large amount of numerical diffusion. So again, in this study, we worked along with GM, and we were fortunate enough to get some experimental data to compare our results. So what I'm showing here is plots of two different speeds. The left one is the 1000 RPM and the right one is the 2800 RPM. And you can see the total amount of oil in the sump as a function of time. So after we run this to a quasi-stable behavior, you'll see that the amount of oil in the sump saturates, and we get to about 0.11 normalized units. And the test data normalized units is about 0.102. So we are very, very close to what the test data predicts, or test data shows, and our predictions turn out to be. And this is the case even at the higher speed. You are seeing that we are at 0.09, and the test is about 0.09 as well. The next one is the oil ejection. So you have a chain that is moving around, and this chain can create oil particles to kind of get pushed through the air vent. So you're looking at smaller fractions, 0 to 0.01. And you can see we have two different baffles and try to see how much oil these baffles prevent from exiting through this fresh air vent. And this is again something that we are fortunate enough to have some experimental measurements. And you can see the amount of oil that we eject out. This is the numerical results, the curve. And we can see that it fairly goes close to the experimental measurements. So what I think these studies are showing us is our VOF capturing is giving us a lot of confidence that in an engineering space, we will be able to do good amount of justice in capturing the realistic nature of the physics while not being very expensive to model such complicated systems. So with that, I want to inform you all that the next webinar will be on July 5th. That's again a Wednesday at 10:30 a.m. And that will be on valve modeling using Simerics-MP+. We hope to see you all again in that version of the webinar. And I'll stop here, and please contact us. You can reach me at cs@simerics.com. And my phone number, the office number here is 248-513-3200. And with extension 263, and I'll be very happy to help you with any of your questions, or you can reach my colleague Varun Nichani at vn@simerics.com. I just give a panoramic view of different VOF applications that we do, and I'll stop here for questions. You can read the questions so that I want to leave the animations on.
Yeah, sure, Chirant. Yeah, we have a question from Anchal. Anchal Vashne. He is asking, the current number was defined as 1. Was it local or global?
It's the global requirement for each cell. The Courant number needs to be 1 so that we can capture our interface very sharply and make sure that we conserve masses for all phases. But for different cells, the Courant number will be different based on how that cell is experiencing the velocity or the size of the cell. So that is what our adaptive time step does. It ensures that we are, making sure that everywhere the Courant number goes to a value of 1.
Okay, so the next question is from Vijit Pawar. He's asking, would the electric motor cooling model work as well with a refrigerant? Please change or real gas effects, the real gas, this thing, the phase change or the real gas effects. He wants to ask that. He wants to know that actually.
I think right now we can do real gas. The phase change is something that we still don't have the capability. So that is something that we'll need to develop. But I think with just wanting to use real gas, I think it should be fairly straightforward.
So any more questions, guys? You can just post in the chat window and then we'll be glad to answer them.
Yeah, please feel free to post any further questions. And if you or any of your colleagues are interested in needing to demo any application, you can also reach us at cs@simerics.com. We'll be glad to do a demo on any capabilities that you require. We have kind of showcased whatever our experience with dealing with different types of volume of fluid approach applications. But there might be some out there that is not been covered here, but it's not that we cannot do it. It's some opportunity that we have to, expand our capabilities so that we can do it. So if you have any applications in mind that you think is suitable for such an approach and you want us to explore it, feel free to reach out to us.
Yeah, looks like the simulation is complete. It has completed 14 seconds. This is what the water level looks like at the end of 14 seconds. And I'm just overlaying the pressure on this ISO surface. We can also create some XY plots. Maybe we want to look at the pressure forces on the walls of the tank. So this is what the pressure force looks like. We can also look for the mass balance. See, so since this is a closed system, basically the mass of water should be constant. Of course, we do have some slight mass imbalance. It's about how much? 0.1. That's still not too bad because it's 0.1 out of 7, right? So it's still 1.4%. So not too bad for, such a coarse mesh and a coarse time step. So still within 2%. Yeah. I think usually these are the parameters we look at, the forces, and of course we want to compare the free surface at different instances of time. So
Yeah, I think this model, the post-processing is very straightforward, but I think what we are seeing here is a tool where you can do everything internal to the tool. So like I mentioned with the CAD integration, we have a preprocessor in different CAD kernels, and that will be something that will be adding on to the software by this year. So you can do a strong amount of pre-processing, then you can do the meshing that Warren showed, and then you can do the solution and as well as the post-processing. And it's a full package that you can utilize very effectively for your simulation requirements. I think this kind of shows how easy it is to set up a model, and it's not some cooked up model. It's actually a realistic tank model of a car, and we can get very good engineering results within a very short time frame. This model runs, like Varun said, 1 second within a minute. We can refine the mesh a little bit, but the runtime probably remains the same. So we run 14 seconds in 14 minutes, which is rapid basically. And that is also an advantage that we want to take with our optimizer. So we can do multiple optimization studies within the same environment. So you do rapidly one after the other to find out the best design point, for example. So those are some ideas that I think is going to be utilized in the future to make the software even better.
Chiran, there's a question from Yashwant. He's asking, is there a module for spray modeling, spray breakup for the animation shown on the top left corner?
We don't have a spray model. We are using the volume of fluid approach to do the spray modeling. It's something that we have kind of devised using a swirl factor and based on the jet velocity and the cone angle. So it is kind of trying to capture the engineering effect of what a spray does to the cooling, because the cooling is of importance in that electric motor application. So we don't have a Lagrangian spray model yet, but this is more like a VOF type spray, which does the job of capturing that behavior. Dikshit, if you can let me share again, maybe I just share the screen once more. Okay, yeah, so this is what I think Yashwant was asking about, and this is what we have done. So we have used so three things were given to us. One was the velocity or the flow rate. We needed to know the cone angle, so that was also provided. They told us that it needs to be a solid cone where you have oil coming in the center and creates a spray pattern of 120-degree cone angle. And we used those three criteria to create our own swirl factor to create this spray basically. It works really well. If interested, I can share this paper and show. So we wrote a UDF to do this essentially.